see what are processes and what are programs and what is the difference between them. So those are two orthogonal concepts. Processes are active while programs are passive or static. Programs is just a file and it is some code written in that file. It stays in the hard disk, but you cannot run it, you can only read it. So programs are passive, they don't run. On the other hand, process is the act of executing a program. So process is dynamic, it's active. So we have to have some way to convert programs and go into processes so that these processes can run the programs. This video will discuss this method of converting programs and using them and using processes to run these programs. So let's go into more details. So a program, when active, can be run by multiple processes. So multiple processes can run the same program. A process can run multiple programs. A program can generate processes. So in the true sense, programs and processes are orthogonal. Programs can be used by processes, programs can create processes, processes can use multiple programs. An example of a process is the start process in the operating system, where a user login opens up the login screen. That is a process. And an example of a program is any C program, any Java program that you might write. So as you can see that programs are written in high level language, C or Java. And processes have to take these programs which are written in high level language, convert them into something that a computer can understand, typically assembly level language or machine language, and then they can run it. So let's see what is the process. What is the process of running a program? Now the simple answer to the question that who converts a program written in human readable language into assembly level language, a simple answer is the compiler. But turns out that the answer is much deeper. It's not just the compiler who converts high level language code into assembly level language. A compiler does that, but partially. So whenever you write a code, let's say you write code using C language, let's take the example of that. In the code you might have certain functions. Now there are two types of functions that people usually write. The first type of function is a function that you have declared in your code and also have defined in your code. So you wrote the function and you wrote the definition for the function, as well as you wrote the body of the function. So this function is in the same C file that you write for your program. The other type of function that you might use is a library function, which means you just call that function. The definition of the function and the body of the function is written in some separate file, which is not a part of the file that you are writing. So there are two types of functions. Now compilers cannot really convert function calls into binary. The primary reason for that being, if we remember the initial videos, maybe the first one, where we said that in order to run a program in our primitive computing system, we need to give memory to that program. We need to have the program in RAM. Now when the compiler is converting a program written in high level language into assembly level language, that program is not in memory. We haven't assigned RAM to the program yet. Now if we want to call a function, and we have seen this before in one of the videos, if you want to call a function, the assembly level language representation of that function is calling the first line of code. So we have to know the address, the actual physical memory address of the first line of code of that function. A compiler does not know that. So if the compiler does not know that, then the compiler cannot convert the high level language code into binary or assembly level language. So that's why the simple answer to the question that who converts programs into binary is compiler, but that is just the simple answer. There is more complexity to it. So let's delve into more details. So let's say a compiler starts converting a program written in high level language into binary. The compiler will only have problems with functions. Now let's consider the first type of functions. The first type of function is the function that is defined as well as written in the file that you are writing. Now whenever a compiler comes to the line where we want to call that function, it has to convert that line into some call address. Now that address is not known to the compiler. So what the compiler does is that it keeps a relative reference for that function. Now what is a relative reference? A relative reference is just a tag. It says that here is a relative reference tag. Somebody needs to figure out where this function is and put the address of that function in that line. Now who is that somebody? The compiler doesn't care. It's something we'll talk about in the subsequent slides. So at this point the compiler doesn't care who converts that line of code into actual assembly level language. It just gives a tag, and that tag is called relative reference. The second type of references or tags that the compiler keeps are for library functions. So the compiler cannot convert library functions as well. So for the library functions, the compiler keeps a different type of tag, and that tag is called the symbolic reference. So symbolic reference is a tag for a function that is not written in your code or in your file. It is written in some library functions, library files. Now the output of this compiler is a mixture of binary and some tags. This output is called the object file. You cannot run the object file because it has tags in it. Tags cannot be run in assembly level language. The computer does not understand tags. So object files or .o files cannot be run. So what next? We have used a compiler to partially convert into machine language, but if we cannot really run it, so there has to be somebody that comes in and tries to resolve those tags and convert them into functions. That somebody is the linker, and the linker uses something called a relocation table. The symbolic references and the relative references are combined into a table called the relocation table. This relocation table says which line of code needs modification by the linker. So the linker can use the object file as well as the relocation table and go to the lines which needs modifications. So the linker uses the relocation table to find those lines and then converts them into binaries. So let's see how the linker works. So before even converting those tags into binaries, what the linker does is that it starts giving memory addresses to the lines of code. Now at this point we haven't given actual physical memory to the program. So what memory addresses will the linker use? For every program, the linker uses memory addresses that start from 0. So if there are two programs that the linker is converting to binary, both the programs will have the same start address, 0. So the linker just arbitrarily assigns the first line of code as the address 0 and then keeps on incrementing the address until it reaches the end of the program. So the whole monolithic program will have addresses starting from 0 and it will be incremented by 1 and the end will be some big value. Now at this point the linker is responsible for two things, the relative references and the symbolic references. So whenever the linker reaches a relative reference, it knows that the code is already converted into binary. The function that will be called in that relative reference is already converted to binary, and it is maybe somewhere down the line. So what the linker does is that it goes to that particular line where the function is already converted into binary and put into the file, and takes the relative address and puts it into that tag, into the relative reference tag. That is the thing that the linker does for relative references, and the linker is done for relative references. For symbolic references, it is a different story. For symbolic references, it has to use the relocation table to figure out which functions have been called, and the linker has to go to the library files, figure out those functions, convert them into binary if needed. Some might already be converted into binary, but copy the binary of that library function and put it somewhere in the code, maybe at the end. Now after it does that, it goes back to that part of the code where it just copied, takes the relative address and then puts it, replaces the symbolic reference tag by that relative address. So again, reiterating, a linker does two things. First of all, goes to the relative addresses. It assigns the relative addresses to the code, and these relative addresses starts from 0, is incremented by 1, and it might end in a very large value. Then it goes to the relative references and converts the tags using the relative addresses of the functions that it has just copied. That is it for the relative references. For symbolic references, it goes to the lines or to the tags where there is a symbolic reference. It searches the function in the library files, copies them, puts them at the end of the code or wherever it wants, then takes the relative address of that particular function and replaces the symbolic reference with that. In addition, the linker also creates something called a symbol table. Now what is a symbol table? A symbol table will tell which lines of code needs further modification. Now what further modification will be needed? So in order to understand that, if you look at the output of the linker is giving relative addresses. Now at this point, the question is, can you run the output of the linker? Can you execute the output of the linker? The answer is no, because the lines of code of the output of the linker do not have any physical address. All these are relative addresses. You cannot use relative addresses to run a program. This is because if you take a relative address and try to run it, multiple programs will have the same relative address. So which line of code will you run? There is confusion. So you cannot run a program with relative addresses. You have to have physical addresses. So if you see the tags that the linker just converted, the linker converted those tags using relative addresses. So if the CPU tries to execute that line where there was a tag and now there is a relative address, that relative address can mean many different things, because every program will have the same relative address space. So that's why it needs some modification. So what type of modification is needed? The only modification needed is we have to convert the relative addresses into physical addresses. The symbol table helps in doing that. The symbol table keeps track of which lines have been just replaced by relative address. Before they were tags and now they are relative addresses. Somebody has to go there after the entire code has received physical memory. Somebody has to go to those tags and change the relative address into physical address. So who is that somebody? That somebody is the loader. So the output of the linker is a exe file. That exe file has the symbol table and relative addresses. You cannot run the exe file. You have to give the loader the exe file. The loader takes the exe file and then what it does is that it invokes the memory management unit, gets some actual physical memory for that program, stores the program into physical memory, updates all the relative addresses into physical addresses. Then it uses the symbol table to go into the lines of code which need modification because they were function calls, and for each function calls it converts the relative addresses into physical addresses. And now your code is ready for execution, but you cannot yet execute it. In order to execute it, what you need to do is you need to start a process. What do we mean by starting a process? Remember, we said that a particular process has a lot of registers: program counter, status register, stack, heap. So somebody needs to allocate the values to these registers. So these registers have to be allocated value, and when the entity that allocates value to these registers is a process. So we create a process. When we create a process, we get values for the program counter, we get values for the status register, we get values for the stack, for the heap, and then we get a process which can run the executable that we just generated from a program. So that is the entire method of converting a static program into a dynamic one where you can execute it through this entity called process. Now the module 2, which is CPU scheduling, will talk about how to manage processes. So a process can have multiple programs, and we have to manage the processes. And by meaning manage, what we mean is that there is just a single CPU because we are using a single processor system. We have to time share between a lot of processes, because a CPU system does not just run a single process, it runs multiple processes. So we have to time share. We have to time share between different processes. So how to time share between different processes? That is what we will talk about in the module 2. Now before we go into those details, we need to talk about different states of processes. So a process has these following states: initial, ready, run, wait, and exit. And this is a typical state diagram of a process. So when the process is in initial state, what it means is that the stack, the heap, the program counter, the status register are still getting decided upon. It's not fixed yet. The operating system has been notified that we want to create a process, but the program counter, stack, heap, all those things have not been fixed. So that is the initial state. Now once those things are all fixed, the process goes to a ready state. So in this ready state, a process is just waiting to be run. Now there is somebody who takes this process which is waiting which is waiting to be run. Somebody has to take this process and run it. That somebody is the CPU scheduler. It's a module in the operating system. We will talk about the CPU scheduler in great detail in subsequent videos. So when the CPU scheduler takes this process from the ready state and converts it into run state, the process is running, which means the program counter of the CPU gets updated and the process executes. Now three things can happen. The first thing that can happen is that the process ends. If the process ends, it goes to the exit state and it exits from the system. The other thing that can happen is that the process can wait for input-output. Let's say the process is waiting for a keystroke. Now if that is the case, then the process gets booted out from the run state and it goes into a wait state. Now when the input is done, the process cannot come back to the run state directly. it has to go back to the ready state and wait for the CPU scheduler to pick that process. That is the second thing that can happen. The third thing that can happen is called preemption. So a process that was running didn't end, didn't go to input output, but still got stopped. A CPU scheduler might decide that it is time for the process to stop and let other processes run in its place. So this process which gets preempted goes back to the ready queue and waits for the subsequent CPU scheduler. In the meantime, other processes that were waiting in the ready queue get picked by the CPU scheduler and they go into the run state. So this summarizes the process states. Now we will use this process state to understand CPU scheduling mechanism.